Hi everybody, it's Mr. Neff. Today I have some kinematic equation examples for you. And does anybody know what's the difference between a cat and a frog? I'll tell you about that at the end of the video. My first example is about a cart that is pushed by a fan. That fan, depending on which way it's pointed, can either speed the cart up or slow the cart down. And it says that the cart starts off at a position of 0. So we're going to say that the initial position of the cart is 0. And so maybe that's right here. It has an initial velocity of positive 5 meters per second. So we'll say that's the positive x direction right there. And so maybe the initial velocity looks something like that. It says there's a constant acceleration due to the fan, but I don't say which direction it is. But then it says the direction to the right is positive and the cart reaches a maximum position of positive 12.5. So of course that would be like over here somewhere. We'll say that this is a final position of positive 12.5 meters. And you might think, why would there be a maximum position? Why doesn't it keep on rolling? Well, it looks like it's slowing down because it says where it begins to travel in the negative direction. So it looks like as we're going here, the velocity keeps getting smaller and smaller to the point where the velocity here, this final velocity for the trip to the right, is 0. Now, what does that tell you about the acceleration? Of course, it tells me the acceleration is negative. It means that the acceleration is pointing back this way. In dynamics, we'll say that it's probably because it's being pushed that way. But anything that's slowing down, the acceleration and the velocity point in opposite directions. Well, we're supposed to find that acceleration. I want you to stop the video here and try to find that for yourself. Okay, I hope you did stop the video. So let me show you how I would do something like this. Good way to start is to say, what are the initial, final velocities, the acceleration, displacement, and time? Now, these are the quantities that could be involved in a kinematics problem. And if you can get 3 out of those 5 filled in, you can use the kinematic equations to get the other 2. It says that my initial velocity is positive 5 meters per second, so that looks good. My final velocity, I had to think about that, but it was 0 because that's where it stopped. I don't know the acceleration, that's what they're asking for. And my displacement, well, I started off at 0 and I went to a final position of 12.5. So my change in position was 12.5 meters to the right. Now, had I started at some other position, then it might have been different. Maybe if I'd have started off at an initial position of positive 1 meter, then the displacement would have only been 11.5 to the right. Time's not involved in this problem. Now, one way to do this is I could just then go over to my formula sheet, look at the equations, and say what formula uses these 3 things and has the acceleration in it. And you'll quickly settle on final velocity square equals initial velocity square plus 2 times acceleration times displacement, like that. And so if you want to find that acceleration, one good way to do it is to solve for acceleration. Final velocity square minus initial velocity square divided by 2 times the displacement there. So this looks like this would be a 0 squared minus a positive 5 meters per second quantity squared divided by 2 times 12.5, positive 12.5 meters. So what do I have there? And I have a negative 25 meters square per second squared divided by 25 meters. That's going to give me an acceleration of -1. I don't want to say I told you so, but I saw that coming. I think you did too. It was pushing over to the left, like we said at the beginning, and there it is. Now, an alternate way that this could have been done is we could have looked at a graph. So we could have said a graph of velocity versus time. Now, how would that look here? Stop the video, try to sketch that. you're going to start off with an initial velocity of positive 5 meters per second, and then you're going to stop. And you're going to go down something like this, okay? Now, I don't know what that time is, time final, I don't know what that is, but I do know one thing. The position, the displacement rather, position change, was positive 12.5. So it turns out that that's this area inside of here is 12.5. And so 12.5 meters there. So I could have said, all right, well then I can figure out that time because I know the area of any triangle is 1/2 its base times its height. So I might say 12.5 meters is equal to 1/2 times the final time times the 5 meters per second. So I could get a final time of 5 seconds. Now, no, that's not what they asked me for. But now I can say, okay, well, if this is happening in 5 seconds, you're going down to 0 in 5 seconds, then what's the acceleration? Well, acceleration is change in velocity over time. So I might say I go final minus initial divided by time. Final is 0, initial 5 meters per second divided by 5 seconds. Hey, I still get an acceleration of -1 meter per second squared. Some of you saw that coming on this graphical approach too, because you saw that once this was 5 seconds, now the acceleration is represented by the slope here. So that means that if, well, I went down by 5 in 5 units, so that could, you may have just realized, hey, -1 meter per second squared as well. Here's my other example today. A little bit harder, a little bit more of a multi-step problem. We've got a race car driver, and they have made a pit stop to refuel. After the refueling, he starts from rest and leaves the pit area with an acceleration of 6 meters per second squared. He does this for 4 seconds, and at that point, he enters the main speedway. So let's stop right there. That's kind of like a problem within a problem there. If the race driver is here with an initial velocity of 0 and accelerates this way to maybe to this point where the final velocity, well, you're going to tell me, I know that the acceleration there was 6, but it's in that same direction. So let's make it positive 6 meters per second squared, and that time was 4 seconds. So what kind of velocity does he build up to in that time? Stop the video, come up with an answer to that. All right, so I hope you're getting to 24, and I got there a couple different ways. You know, just thinking of regular old TV chart, I might say, hey, since I know the acceleration is 6, that's what I'm counting by. So my velocity started off at 0, and then I go 6, and then I go 12, and then I go 18, and then I go 24. You could have done that with an equation too. You could have done the acceleration is final velocity minus initial velocity divided by time, and solved for final velocity and got that 24 that way. However you get there, I have a final velocity of positive 24 meters per second. Now, you read more. Then it says there's another car. As this driver enters the speedway with this velocity, there's another car that's zooming by. And this car is moving at 70 meters per second, so it's quite a bit faster. That velocity is going to be maintained. If you read forward in the problem, this 70 meter per second car I drew in red passes that blue car. They maintain that speed, but of course, they are going to zip right by them because they're going much, much faster. Now, the blue car, though, has an advantage because it's going to continue to accelerate, which means that for a while it's going to be left behind, and then it's not going to be left behind anymore. It's eventually going to catch up, and well down here, way farther than I'm showing, the two of them are going to be side by side. Again, the red one will still be moving at 70 meters per second, whereas the blue one is going to have to be moving way, way faster than the 70. So a velocity that's well greater than 70 meters per second. If they only move at 70, then at that point they will just stop getting behind, but they won't catch up. Okay, well, I'd like you to stop the video, and I'd like you to try to decide how much time it's going to take for these two to catch each other. All right, well, I hope you stopped that, and I hope you tried that. You might say, boy, there's a lot going on here. And you're not kidding. There is a lot going on here. The nice thing that I notice is that the two displacements are the same. And so this blue one is going to go delta x, and how far is that? Well, that's VOT plus 1/2 AT squared. And so that's going to be equal to 24t plus half of the acceleration, which was 6 times the time squared. The red one, on the other hand, is just maintaining, and so you could theoretically say VOT plus 1/2 AT squared for it, but the acceleration there is 0, so that whole term goes away. So this is just delta x equals 70t. Now those two are equal to each other, so I could say 24t plus 3 half of 6 t squared is equal to 70t. And if I bring everything to the same side, I could, here, I'll do it in purple because it's the combination. 3t squared minus 46, that was 24.0, so 46.0t is equal to 0. Now, solving that, you have choices. Well, something that I like in this kind of case is to factor out a t. Get rid of that t right there. That got factored out. Now, I got two things equal to 0, and so the solutions are when each factor is equal to 0. So t equals 0. I'm actually comforted that that's there because at the very beginning of the problem, they were side by side. They had the same displacement. But I'm more interested in later on. 3t minus 46 is equal to 0. So 3t equals 46. It looks like t is going to be 15 1/3 seconds. Not all those are significant. So down here, this is going to happen at 15.3 seconds. There you go. There are other ways you could have done it too, especially graphically would have also worked. All right, I hope you were able to follow that one, and if not, give it another shot. And what is the difference between a cat and a frog? A cat only has 9 lives, but a frog croaks every day.